Let's go through the answers to the practice problem worksheet that I gave you for 7.1, 7.2, and 7.3. We're looking for the three things for each of these elements. First, the number of valence electrons. Second, I need the dot structure. And third, I need the chemical symbol of the ion, which looks a lot like the chemical symbol with just a charge added. So let me write my answers over here. For 1A, the first part would be 2 valence electrons because barium is in group 2. Then I write the dot structure, and you can write it like that. Oh, sorry, Ba, not boron, there we go. Barium. Then I need the ion chemical symbol. So that's the barium, but it's going to lose these 2 electrons and end up with a positive charge. So there's the complete answer for barium for number 1. A. B. Now let's look at iodine. Iodine is a halogen, so it's in group 7, so it has 7 valence electrons. Let's distribute those Lewis dots. 1, 2, 3, 4, 5, 6, 7. So there's the dot structure. Again, I'm not taking points off for where you've located your dots, just as long as you have pairs on the tops and bottoms, or pairs on 3 sides and a single one on a 3rd side. So what was the ion going to look like? Well, it's iodine, and it's going to gain 1 more electron in order to get to 8 valence electrons. So I have a iodine 1- charge. Yes, it is okay if you leave off the 1 and just put the minus, but I want to be clear that it is a single negative charge. Part C. Now we're doing potassium. Potassium is in group 1, so it has 1 valence electron. The dot structure would be K with its 1 electron, and it's going to lose that electron and be left with a positive charge, so K with a 1+ after it. Again, you can leave off the 1, that's okay, that's what they mean. It's a single positive charge. Number 2, how many valence electrons does each of the following atoms have? Well, gallium, what group is it in? It's in group 3, so it has 3 valence electrons. Fluorine is in group 7, so it has 7 valence electrons. Selenium, I'm just looking at the answer key and it says 6, so I'm guessing it has to be in group 6, because it has 6 valence electrons. Great. Number 3, how about the electron configuration for calcium? Well, let's see. Some of you chose to do the noble gas, and then whatever's left after that, I'm going to actually do the whole thing out so you see the process. 1s2, 2s2, 2p6. How many electrons is that? 2, 4, 10. Okay, so I'm up to 10 electrons. I need more than that to be calcium. I need 20. 3s2, 3p6, and 4s2. So I got 10 here, and I got 10 more here. It's 20 electrons. That must be calcium. And note, we are not using the ion form. Part B, the chlorine. Chlorine is going to have the same kind of thing. We start with the 1s2, 2s2, 2p6, but I only have 17 electrons for chlorine, I believe. So 2p6 and then 3s2, 3p5. So it would love to have 8 electrons, but it does not. It is its native element. Then sodium, but this one's an ion, and if it's a positive ion, that means it's lost one of its electrons. So how's this going to look? Well, we've got all of these first ones. Sodium is supposed to have 11, but it's lost one, so I only get 10 electrons for my electron dot structure. So here's 2. Now I've got 4 electrons. Now I've got 10, so I have to stop. The last electron that was going to be in the 3s1, that's gone because we got a positive charge. So that is the correct answer for C. D, phosphide. If you see IDE, that means it's an ion. So it's the ion version of phosphorus. Phosphorus is born with 15 electrons, But if it's the ion, that means it's done its adding or subtracting of valence electrons. So look at the table. You see phosphorus is in group 5A. That means it has 5 valence electrons. It's going to opt to get to 8. So it's going to add on 8 more electrons. I'm sorry, add on 3 more electrons in order to get to 8. So what we've got would be the 1s2, 2s2, 2p6. So there's my first 10. Phosphorus starts off with 15, but it's going to gain 3 more. So now I got to account for 18 electrons. So here's 10. I keep filling, always in the same order. 3s2, 3p6. Oh, and there's 8 more. So here's my first 10, and now I got these 8. And chlorine has a full outer shell highest energy level of electrons. And lastly, oxygen with its charge of 2-, meaning I've included some extra negative charge that comes from adding electrons. Oxygen is in group 6, so it starts with 6 valence electrons. The ion version gains 2 more, giving me 8 in the outer shell. All right, so 1s2, 2s2, 2p6, there's my first 10. And that is all you need to write for the oxide electron configuration. Number 4. What's the relationship between group number of representative elements and the number of valence electrons? Group number equals valence electrons. Number 5. How many electrons will each element gain or lose when it forms an ion? I'm just going to write these out. If you have questions, I'm pretty sure most of you have done this already, so you're just checking your answers. So, loses 2, and therefore is a cation, meaning it added some negative charge. B is aluminum, loses 3, makes it a cation again. We're left with positive charge. Did I say that right for the first one? Okay, letter C, tellurium. Tellurium is in group 6 probably, yep. So it's going to add 2 and become an anion on the right side of your table. Letter D, rubidium is over on the left. No, that was radium, sorry. Rubidium should be, oh yeah, it is on the left, just below potassium. So it will lose 1 electron, therefore it's a cation with positive charge. E is bromine. Bromine is one of our halogens. It will add 1 electron and become an anion. And F is phosphorus. Phosphorus is in group 5, so it will add 3 and be an anion. Number 5, how many electrons will each element gain or lose in, oh, just did that one. Number 6, give the name and symbol of the ion formed when chlorine gains 1 electron. Well, this would be chloride, and the symbol would be Cl, and I'm just going to write the minus and skip the 1. Potassium loses an electron. Potassium is a cation, so we don't change its name. So it's still called potassium, but its symbol does change to K+. Oxygen, that's a nonmetal, that's on the right-hand side, that does get a name change, oxide. And that would be O2- because we've gained 2 electrons, we've increased the negative charge. Barium, losing 2 electrons. What do you think? Baryide? No. It's the metal, it's the cation, it doesn't get a name change. How many electrons are lost or gained in forming each of the following? This magnesium has a charge of 2+, so we have lost 2 electrons. Bromine with a negative charge means we've gained 1. Silver has a 1+ charge, meaning we've lost 1 electron. and iron with a 3+ charge means that we would have lost 3 of its electrons. Classify each of the following as cation or anion. Positives are cat, negatives are anion, positives are cations. Okay, next. Okay, section 7.2. We're going to use the electron dot structures to predict these formulas. Sodium has a single electron, bromine has 7, it's in group 7. Now notice how I've left the one single bromine dot right on the same side that would connect like Legos, as Dan McKinney pointed out, connect like Legos together. So sodium will slide right over and give up that electron to bromine. Bromine's happy, sodium's happy, and I get sodium bromide. Sodium with sulfur. Well, we've got one electron from sodium, but sulfur has room for 2. So let me write the dot structure here. So this sodium can slide over and be Legos again, giving up that electron to this side of the sulfur, but I need another sodium over here with one more electron to connect and make sulfur happy. So for every sulfur I've got, I actually need 2 sodiums. So we call this Na2S, sodium sulfide. The subscript 2 goes is the number of atoms you need of the thing that immediately precedes it. So the 2 is stuck on the sodium. So we got 2 sodiums and then 1 sulfur. How about calcium and iodine? Calcium has 2 electrons. Put those in the wrong spots. Here, I'll fix that. Calcium has 2 electrons to give up. Iodine has room for 1. Ooh, now what? Well, it's sort of the opposite of the sodium sulfide. Calcium can give up this one right here to the iodine, but it's still left with 1 more. So let's get out another iodine and put it on this side. And now we see that these electrons, 1 from iodine, 1 from calcium, those will be a pair around the iodine, giving that 8 and taking away all the valence electrons from calcium. So this means I got 1 calcium and 2 iodines, and I call that calcium iodide. Letter D, aluminum with oxygen. Aluminum has 3 electrons to give. Oxygen has room for 2. So how can I match these up? This ratio problem, aluminum and oxygen, is kind of hard to represent with the Lewis dot structures. I'll give it a shot though. Let me make a line of oxygens. And the oxygens aren't bonding together, but I'm just drawing them this way so that you can see kind of easily how we would set up the electron dot structure version of this aluminum with oxygen bond. So every time there's an oxygen, it has 2 electrons that it's trying to add on. 1 here, 1 here. Aluminum has 3 electrons that it would like to give up. So I'm going to write an aluminum right here. And I'm going to do a really crazy thing with the Lewis dots. I'm going to put the 3 aluminum dots sort of around this side, and over here, 1, 2, 3. Because why? Because this dot can now go over here. This one goes here, and this one goes down here. Same with this. Aluminum, this one goes here, this one goes here, this one goes here. So this is one way to write the aluminum oxide electron dot structure. This is a 2-dimensional thing, and it is a very 3-dimensional problem, but at least you can maybe see that these line up with ratios of 2 aluminums and 3 oxygens. So I would write Al2O3 and call that aluminum oxide. Moving on, Number 2, which of these combinations of elements are most likely to react to form ionic compounds? Well, ionic compounds are formed when metals react with nonmetals. So, is sodium a metal? Yeah, okay, great. Is magnesium a nonmetal? No, it's not. Magnesium is also a metal. So I got a metal with a metal, not an ionic bond potential. Sure, I guess we can bond those two with using some, say, metallic bonding, but that's not what the question is asking. So this one, sodium and magnesium will not be ionic compounds, will not make an ionic compound. Barium, that's a metal. Sulfur, non-metal. Hey, okay, so that would be one because ionic bonds form between a metal and a nonmetal. Potassium, that's a metal. Iodine, that's a nonmetal. Ooh, so I got it. Oxygen, nonmetal. Argon, noble gas. That's not one of them. Number 3, what's the meaning of the coordination number? Coordination number is simply the number of ions of opposite charge that surround an ion in a crystal. Where can I put this? I will try to squeeze it in here. Number 3. Coordination number is the number of ions of opposite charge surrounding an ion. And we can also be specific here and say it's in a crystal, because if they're in a solution, this doesn't matter at all. So coordination number is the head count of opposite charged things. So if we looked at, say, the barium and the sulfur, and I'm looking at how many bariums are around the sulfur, I can tell you that the coordination number for sulfur would be my count of bariums. Number 4, how is the coordination number determined? We use X-ray diffraction crystallography. Patterns are used to calculate the positions of ions in the crystal and define the structure. So you can just write X-ray diffraction. That was part of the passage in your book. Last, section 7.3, bonding in metals. What is a metallic bond? Well, we've got cations surrounded by valence electron C. These valence electrons can move around. Okay, how is the electrical conductivity of a metal explained by metallic bonds? This is a really long answer and I don't have a lot of room here, so let's just say that the electrons are easily moved, which creates current. Are metals crystalline? Yes. What does crystalline mean? Well, they are, you know what, let me zoom in and then I can write a little bigger here. They have an compact, orderly structure. Give 3 possible crystalline arrangements of metals and describe each. Well, we've got face-centered, cubic, body-centered cubic, and close-packed hexagonal. And then the description I need here is that for close packed hexagonal, 12 atoms. Now, if you're thinking that this idea of how many atoms I have around each one is a little bit like a coordination number, yes, it is, except that with metals, when I'm talking about this close packed, body-centered cubic stuff, they're all the same element. So if I'm doing manganese, then it's all manganese ions, or whatever it is, they all have the same charge because they are all cations in metallic bonds. So a little bit like a coordination number, because I'm looking to see how many things it's sort of touching, sort of bonded to, but not an opposite charge thing. Coordination number needs the opposite charge. So close packed hexagonal has 12 neighbors. Body-centered cubic has 8 neighbors. And face-centered cubic has 12 neighbors. Then, what's an alloy? Alloy, just like in your book definition, is a mixture of 2 or more metals. Name the principal elements present in each of the following alloys. This stuff is stuff you should know, and I will hold you responsible for it on quizzes and tests. So, brass is made up of copper and zinc. Ooh, you know what? I'm going to use the chemical symbols here. So, copper plus zinc. Bronze is copper plus tin. Stainless steel is mostly iron, but we also add chromium, carbon, and nickel. I'll write these answers down here. Sterling silver is silver plus copper. Cast iron is iron plus carbon. Yesterday we talked about wrought iron, which was also iron and carbon, but in different ratios. Lastly, spring steel, which is what your car's springs are made of, iron plus chromium plus carbon. So these things are good alloys that you should know for the rest of your life, and those are all the answers that you need for this section. Thanks.